If you have the scenario where you are spinning with respect to y, with respect to x, the ultimate judgment call is going to come to you. You are going to decide the easier option of the two. If you make the wrong choice, finding the solution is going to be hard. Sometimes you just can't do it, right? But never say never. Okay, I'm going to take that case. I'm going to spin. The cross-section of the solid, we don't know what the cross-section is, correct? Okay. What am I thinking? I could do anything for a Klondike bar. Don't know that one?
No, everyone you say it.
Huh? Okay, regardless, do we know what a Klondike bar is? Okay, I take that bar and I start slicing. I've got thin slices, yes? Now, whatever shape that I have is retained throughout each cut. Do you agree? Okay. If you have what other, I don't eat that much ice cream, but one of those frozen cone things.
Drumstick?
Oh, a drumstick, that's the one. You've got a drumstick, right? Start cutting. Does every single section that you cut, does it look the same? No. If I'm going to give part of my drumstick to someone else, I'm taking that part, giving that to someone else. Assuming it's this way, I get the bigger portion, right? So it is not going to be the same. What is deciding the cross-sectional area or whatever piece that you take? Drawing this helps. I am no artist, but it does help. Recall that strip thing that I was referring to a long time ago. Yes? Okay. I am going to try and draw this. That's one cross section. Yes? Another cross section. Good. As I move this disc from here down that way, does it look the same, the disc, the flat disc? No. Wider, getting narrower. As this moves closer and closer, the disc is going to get smaller. Do we agree? So as you move along, this area is bigger than that, that's bigger than that. Yes? Where did I start? I started with this strip, which is right here, spun it around, I ended up getting this surface. With me so far? Okay. Disc. What is the shape of a disc? A what? Sorry? Circle. If it had some thickness, still a circle. Agreed. Okay. So I would want to know, ignoring that thickness for now, if I simply have a disc, what is the area of that disc? That's an easy question. Where is that sound coming from? Sarah, go ahead.
Length times width. Length times width.
Length, well, length times width is for rectangle. I'm referring to a disk.
Square.
Hi, is Google telling you? Bing.
No,
What's
I
his
didn't
name
look,
with
I didn't look.
Driving me crazy. Don't you? Well, recorded. Hopefully they don't sue me, but freedom of speech. Pi, what is the next bit? R squared. What is R?
Radius.
Radius. That entire expression is the area of a circle. Okay. Going somewhere. Oops, not a circle. Still not a circle, but will do for this driving. Good. Area, pi r squared. Take that, tilt it this way, still a circle with me. Okay. I'm going to add some thickness to it. Good. Pi r squared is the area. That's the tricky part. Okay. So it's not a circle within a circle, but think of a wedding band. Right? It's got some thickness to it. This is the thickness going around your finger, or any ring for that matter. So this circular object with some thickness has a volume, right? With me? How would you write that?
Isn't that just height?
Huh?
Isn't that just height?
I erased that formula, but what was that formula that I started with?
Area times.
Area times height. Agree? In this case, I don't have height, rather I have the thickness, right? Up becomes the thickness. Area times thickness. Integrate, in other words, take this, move it along, add them all together. I got my volume. Agreed? Okay, so I need to know area. And it all goes back to this. You're spinning, so you are forming something circular. It's going to have pi. Good. That dx will go to this tiny strip. That is your dx. Good. All that is missing is the radius. I find the radius, I am done. Agreed? Well, what is the radius? For that case, just to be precise, for this case. Let's go there and then we'll come back to you.
It's the Riemann sum of the unspun function.
Riemann sum of the unspun function.
See how it's Riemann sum?
Well, if it is a Riemann sum, you're getting an area. It's no longer a radius. I forget your name.
Yes, Anya.
Yes, Anya, go ahead, and then we'll go back to Lorenzo.
From like where the curve is to where the axis is, because that's like the halfway the radius, right?
Very good. Did you follow what Yesenia said?
I'm like looking at it too, but
I'm spinning it this way, right? So the radius is there. Where is that radius? From here to there. Agreed? Yes? Okay. I drew that for a reason. I asked the question for a reason. I drew that for a reason. Look at those and tell me what defines that radius at any given place I place that disk.
Y value,
Very good. What? I forget your name.
George?
George. George says Y value. Do we agree? This is the key part. That's why I'm taking time to explain this. Are you with me? So y equals x squared. Good. Dotted line just for reference. Just a circle. Of course, it is going to have a thickness defined by dx. That will be my strip. The radius of this circle, poorly drawn circle, I'm no artist, is either from here to there or there to there. Agreed? Good. I'm going to pick that. This is arbitrary. So I pick that point. I would like to know that length. Yes? Okay. Give me a number between 0 and 10.
4.
Very good. Who said 4? Read my mind because I had 4 in my mind. So 4. And I ask you, well, what is the radius at that point? What is your answer? 16. Okay. Move that circle over. I come here and I ask you, well, pick a number.
2.
2. That wasn't creative, Raphael, but I was thinking of 1, so it doesn't work. 2. What is the corresponding radius? 4. Give me a letter.
D.
What?
Is it D?
D. Give me a letter other than D, X,
2,
Y,
2,
T. Okay. So now I'm going to pick some arbitrary T. I'm going to put it right here. I would like to know when X is equal to T, what is the radius?
T squared.
Louder, Caleb.
T squared.
T squared. Good. All of these numbers, how did you give me the answer? What did you do?
Plug it into the function.
You plugged it into the function. So as I move this thin disk or circle down this way, its radius is changing. How is it changing? It is changing with respect to this function. Agreed? So you are using this function to find the area. With me? Okay. I'm going to use the same function to find its volume. Are we clear? So I started with area times height, thin disk, hence delta x, thickness of disk, moving it over that interval, hence integral, infinite sum, slices of Wonder Bread from last time, organic, gluten-free, add them all together, get the loaf of bread. In this case, funny looking loaf. With me? Okay, so time to find this area. Raphael picked 4 for us. Can I erase this one? The picture that I'm about to draw is something I strongly recommend that you do too. Doing this will help you not make mistakes. It will tell you about or what letter to use. You're integrating with respect to which variable, all of this. So the function that I'm going to use is y equals x squared. the interval over which I'm going to find the volume is from 0 all the way up to 4, A to B, which is why we needed definite intervals. In my head, because of practice, I can visualize the shape, but I strongly recommend that you do this so that you can visualize too. I'm not drawing just a line, rather I'm drawing a thin strip to indicate that is the thickness of that cross-sectional disc. With me? So, for that dx, going to move this along that curve. So, y is equal to x squared. Erase this part. Okay. The radius is going to vary with respect to that function. So it is only fair for me to write the volume as integral. Radius is varying with respect to y. So pi, instead of the letter r, I'm just putting 1. You all gave me the answer. When I plugged in x is equal to 4, when I plugged in x is equal to 2, when I plugged in x is equal to t, you said, well, it's just whatever I plugged in, y. Well, then why not use y? Agreed? Okay. Radius defined by y. But what is y? I'm integrating with respect to x. So
Y is x squared.
y is simply x squared. Here is another important tip. Anytime you have exponents, what should you do? You have exponents. True, but before that, this is like a tip so that you don't make mistakes. I mentioned I am a proponent of something. Starts with the letter P. A-R. P-A-R. E-N. It's got parent in it. Parentheses. Okay. Important. Same with functions. I don't know why your book doesn't use parentheses here. Pet peeve. You should put parentheses. This way you don't make mistakes. When you write ln of x, parentheses, e raised x, parentheses, exponent, parentheses. Put parentheses everywhere. So, pi, x squared, x raised 4, dx. Going from 0 all the way up to 4, agreed. This strip is moving along the x-axis, 0 to 4, 0 to 4. Pi is a constant, bring it out. What is the integral of x raised 4? That you should know by now. Plug in the lower limit, plug in the upper limit. So you have pi 4 raised 5 over 5 minus 0 in there, 0 raised 5 is 0, divide by 5, 0. 4 raised 5 is 1024. So the answer is 1024 pi divided by 5. going to consider the same curve. Yes. 0 to 4 along the x-axis. I'm going to spin it about the y-axis. I want you to find the volume of that object that you get by revolving this curve about the y-axis. What is the first step and where should you start? The most important thing, I started somewhere when I drew that picture. The first thing that you've got to draw after you draw the curve is
revolutions with the mirror on the other side.
very good. That's one. Alex says put the mirror reflection so that you know what type of shape you're going to have. Great. Next thing I drew. 5 little words. Start with S, ends with P.
A little strip.
The little strip. Right? You have to draw that strip. Let's see if you can draw that first, and then we'll go from there. Give it a try. We'll see. We're almost there. Okay, I am spinning about the y-axis. I'm going to draw this dotted line for reference. So that is my curve, right? Going this way. And I've got to put the disk. So the strip is going to define the disk. Again, think of Wonder Bread. Bread is horizontal, slices of bread, yes. Slices moving across, you are stacking slices horizontally. Good. Flip that bread. You are laying slices on top of each other, correct? So each slice is moving along which axis? X or Y when you lay it vertically? Y. So the slice is moving about y-axis, so the strip is moving in this direction. Good. If X can go only from 0 to 4, what are the bounds for Y? It can go from 0 to 16. Because I told you the curve is Y equals X squared. With me so far? So I said knowing the strip matters because go back to how I started writing things. I put the integral, the thickness first, dy, correct? The strip is moving along the y-axis, okay, 0 to 16. I have a pi in the formula, put pi there, good. This is an easier way to remember things. If you are integrating with respect to y, whatever function that you have in the integral has to be a function of y. Do you agree? Yes? I have y equals x squared. Y is a function of x. If that relation is 1-to-1, which it is, how can you write x as a function of y? What is that? If I took the square root on both sides, root y is x, correct? Where's that? What I started with is here, y equals f of x. X equals g of y, correct? I need a function that is in terms of y for me to move that along the y-axis. So this is the function that will go in here for the radius, correct? So root y, square the radius. Good. Pi 0 to 16. What is square root of y squared? Just y. So y times dy. What is the integral of y?
Y squared over two.
Y squared over 2. Plug in lower limit, plug in upper limit, 16 squared divided by 2, 256 over 2. Lower limit, 0 squared over 2, which is just 0. What is 256 over 2? 128. The answer is 128 pi. Good.